lecture. So we are going to look at well, the structure of percolation clusters when we are in the supercritical regime. So from now on, when theta p is equal to 0, okay, when p is smaller than pc, I will say that we are in the subcritical regime. And when p is larger than pc, we are in the supercritical regime. And pc is just a critical threshold for percolation. So, okay, so here I'm going to assume something a bit weaker than p larger than pc, namely that theta p is larger than 0. Okay? Remember that we don't know what happened exactly at pc. And the first thing we are going to do is to prove that we have only two possibilities for the number of infinite connected components. Either it's equal to 1 or it's equal to infinity. And actually, this proof is quite general, and I'm not going to use much on the structure of the graph. So in particular, it's also valid on tree, but yeah, I'm not even using the fact that I think I'm not using the fact that the graph is periodic. So maybe it could be also true on an arbitrary graph. Okay, so what we had seen last time is that well, because this variable is a translation invariant, so because the event z is equal to k is invariant by translation for every k, then it has to be almost surely constant. Okay? So now we have to show that this constant cannot be a number between 2 and, it cannot be a finite number which is larger than 2. Okay, so maybe before I start, are there any questions so far concerning what we did last time, what we did before, or the exercises? Okay, so let's start with this. Okay, so here, maybe it's more comfortable if you so let's assume, that P of z equal k is equal to 1 for k in 1. N. Okay, I don't know if for you n contains 0 or not. I'm not sure what it is for me, so. But for k larger, for k larger than 1, and strictly smaller than infinity, and we are going to show that if this holds, then k is equal to 1. Okay, this is all what we need to do here. Okay, because we already know that. There exists k such that p. This is what we want to show. Okay. So now I'm going to use this notation for the box minus n to the d. Okay, and I'm going to use this notation for the internal boundary of the box. So these are the vertices of lambda n, which are adjacent to vertices that are in the complement. Okay. So what I'm going to say is that if I have finitely many infinite connected components, then there exists an n, random, okay, which is such that all these components touch the box gamma n. Okay? So this is just to say, okay, I take, say, n of omega, which is equal to the mean of inf x infinity x in ci I in 1 k. Okay, where C1 ck my okay, I have finitely many components. For each of them, well, there is a point which is closest to the origin for the infinite norm. Okay. Okay, here I should put max. Okay, so now if I take n which is larger than the maximum of these infimums, then it means that yeah, I will touch all the components. Okay, so in particular, okay, what I have is that well, the limit when n goes to infinity of the probability that gamma n touches all k components is equal to 1. Okay, because this is a sequence of increasing events, and I know that the union has probability 1 because of this. Okay, so in particular, I can find an n such that this probability is larger than 0. Okay, so okay. Now heuristically what I want to say is, in this sense, in a sense, this event looks like something that is independent of what happens inside the box lambda n. I'm going to tell you in a second that it's not really the case, but let's assume that for a moment. So therefore, it's independent of the state of the edges here. So just modifying the probability by a constant factor, what we can do is open all the edges in the box. Okay? And if we open all the edges in the box, then we have only one connected component. All the infinite connected components that touch the box, and they are all connected together, okay? Because any point in the boundary of gamma n is connected to another to the other point. Okay, just using these inside edges. Okay, so we have to be a bit more careful here. So let me write an event which is an event which includes this one, and really only depends on edges outside of lambda n. Okay. I cannot read myself, but this will be fine. Oh, yes, okay. So let be Cn the event. Okay, so. Okay, so let En be the set of xy in E such that xy is included in gamma n. Okay, and En is just E minus En. Okay, so let me denote Cn now, the event. There are no infinite components in omega restricted to En that do not intersect gamma n. Okay, so now I will claim that, okay, so now the thing is that, okay, if I call this event Bn, what I have is that Bn is included in Cn. Bn includes Cn, sorry. Okay, so if Bn occurs, basically, then all the infinite components in the percolation process, but which is restricted to the edges outside of the box. Okay, so now I'm just looking at a graph, but with a hole in the middle, and I look at the percolation process for this. Okay, so I know that all the infinite components for this percolation process, they have to touch the box. Okay? If this happens, then this happens. This seems very reasonable, and you can really check that this is true. Okay. Now, the way I've written this is clear that this does not depend on the edges En. Okay, it only depends on omega restricted to the complement of En. Okay, so now what I can say is that if I look at Z equal 1, then this includes, okay, so this gives me, okay, I'm messing up with inclusions here. Okay, so here, yes, Cn is okay, Bn is included in Cn. Okay, if this occurs, then this occurs. Okay, so in particular, the conclusion is that the probability of Cn is positive. Okay. Now what I have is that if Cn occurs and all edges in En are open, then z is equal to 1. Okay? Basically, I know that all the connected components I have in my system, they touch the box. And I know that all these connected components, all the infinite connected components that I have in my system, they touch the box. And I know that everything that touches the box is only one component because everything in the box is connected together. Okay, and now using independence, okay, the fact that, well, the omegas on the edges are independent, and these depend on distinct set of edges. Well, I know that this is equal to pp of Cn times the probability of this, but the probability of this is just, well, p to the power the cardinality of En. Okay, just using the fact that these variables are independent Bernoullis. So n a priori can be very large, but this is not important. I just want to know that this is positive. And then because I know that this has probability either 0 or 1, this implies that okay, and so we have proved this claim, and this claim implies this claim. Because if this does not occur, and theta p is positive, then z cannot be equal to 0, so it has to be equal to infinity. Okay, so any questions so far? Okay, so really the next step is probably the hardest result we have seen so far. With what we are going to prove is that on ZD, this actually always occurs. Okay, and it relies on a very smart geometric argument, which is due to Burton and Keene. So maybe before doing that, we'll do something much easier, which is to show that this is what always occurs for regular trees. Okay, so let me write this. Theorem. On TD, we have PP z equal infinity is equal to 1 when P is larger than 1 over T. Okay. So would anyone have a suggestion on how to prove this? Okay, I'm not saying it's easy, trivial or even easy. It's just that it's much easier than what you have to do in the ZD case. But this gives you a good amount of information. So maybe you can try to prove something which is much weaker than this. I mean, you just have to prove that this doesn't happen. This is the only thing you have to prove. Okay, so we have prove that pp z larger than 2 is positive. Okay, so now, is there any ID for this? Okay, so let me draw the tree. Okay, let's take d equals 3. Okay, so maybe there is an easy way to have at least, to make sure that you have at least 3 infinite connected components here. So first thing you would like to do is make all these edges closed. Okay. And then make sure that V1 is connected to infinity, V2 is connected to infinity, and V3 is connected to infinity. Okay, so let's look at this event. So it's a probability that, okay, let's remember that these edges, I call them E1, E2, E3. So probability that Z is larger than D, it is larger than this. So probability that for all I in 1 D and VI is connected to infinity in TVI. Okay, well, you remember these are the subtrees that grows from VI. Okay, so now all these events here that I've written, they depend on, okay, all these things for different i's, they depend on different sets of edges, which are not these ones as well. So the probability of this is equal to 1 minus p to the power. Okay, here it's d plus 1, I guess, because my tree is d plus 1. Okay, and this is the same as the probability that the root is connected to infinity in TE. And, well, this is positive. Okay, if I call this theta p, if you remember what we saw last time, theta p positive, it's equivalent to theta p positive. Okay, so we are sure that, yeah, we have more than 2 infinite components with positive probability. So therefore, the only possibility is we have infinitely many of them. And I mean, somehow if you want to track these components, okay, here we are formally using this theorem, but intuitively it's kind of clear that with this you already have the information that you would have many more components, because if already starting from the root you start to find some, then it's kind of clear that things are going to split higher up. I mean, it will be very difficult. I mean, as soon as you have a closed edges, basically you create a new independent tree there where you have a positive probability of seeing a new component appear. Okay. So in order to prove that z is equal to 1 on ZD, basically we need to use a probability which is true for ZD but not true for the tree. Okay, so for the first time we are going to use something beyond just having a periodic lattice. Okay. Okay, so I don't know if what I'm going to say makes any sense, but let me try. So basically, the idea is the following: is to say that okay, basically, if you have infinitely many components, okay, then when you start an infinite component, it will have to exist somewhere on the boundary, okay, within a box. And the idea is that basically we are going to find an argument that tells you that there is not enough room on the boundary for all the infinites, for all the components to exist. So it's really a geometric argument that rely on the fact that the volume of a box is much smaller than the volume of its boundary. Okay, so this is really the property of ZD that we are going to use here. Okay, and okay, with what I just said, it's not exactly clear, okay, why there is not enough size on the boundary to exist. So we have to find a clever argument to make to justify this. Okay, so let's assume that z is equal to infinity, p almost surely, and find this contradiction. So what's going to happen is that for n sufficiently large, okay, I will make sure that I have at least three distinct for n large gamma n intersects three different infinite components with positive probability. Okay, and I can say even more. It intersects more than three. Let's see. I think it's 3 plus. Okay, how many vertices do I have? Okay, 3 plus 2 to the d. Okay, I can make this number arbitrary, but what I want to make sure is that basically, so at least 3 of them do not touch the corners. Okay, I want to make sure that these infinite components intersect outside of the corners. Okay, this is for a technical reason, but okay. So this is true, just the same as before. Okay, I take well, the 3 closest infinite component to the origin, and well, if I take the minimum distance of these, this is something finite. So in particular, this means that the probability that this happens goes to 1, 1, and goes to infinity. Okay, so now I want to do the same thing as before. I want to transform this Bn into an event Cn that does not depend on what happens inside the box. Okay, so which touch let me call it okay, maybe Dn, so that you don't have and this is I don't know. Okay, that's Dn, this is Fn. Okay, so now I know that Dn is includes Fn. Okay, so that's the probability outside of the corners. This is a minor point. So what I get is that pp of fn is positive. And now I want to use this to define another event that has positive probability. So here's the event I'm going to look at. So we're going to introduce a definition, which is what is for x to be a trifurcation, okay, for omega. So for x to be a trifurcation, what we mean is that x is adjacent to exactly 3 open edges. Okay, so the number of y tells that y is a neighbor of x, and omega xy is equal to 1. This is exactly equal to 3. Okay, and the other thing I want to say is that, okay, let me draw a picture. So basically, I want x to be connected to infinity in 3 different ways. So it's connected to 3 neighbors, okay? And I want these 3 neighbors, okay, they are connected to infinity. But if I look at the connected component of, okay, so this is y1, y2, y3. Yes? So, yes, if I want this to be true, it has to be the other way around. So that's a bad reason, but that's the first reason. And let me see. Yeah, so if this happens, yes. And this inclusion, by the way, it's strict because this component could be distinct for this environment, but here I'm not using edges inside the box. So if I use edges inside the box, maybe these things are connected together. Okay, so thank you. So, and always worry about any inequalities you see in this class. They might be in the reverse, so position. Okay. Thank you. Okay, so what I mean now is that if you look at the connected component of the y-i's, but they are not, which are not allowed to use these 3 edges, then they are distinct. So y1 the 3 neighbors of x are in distinct infinite clusters for omega okay, minus star, okay, x, where E star x is equal to E minus the set of E such that x in E. Okay, so if I now look at the percolation process, but I disallow the use of edges that are adjacent to x, then these three things are indistinct in field components. So what I mean that there are no connection between these things. Okay, and this is what I call being a trifurcation, and this notion of trifurcation, it will be only used in this proof so far. Okay. So now what I want to prove is that with positive probability, 0 is a trifurcation. Okay, so basically now you see that showing that Fn has a positive probability, it's kind of a good preliminary because Fn is independent of what happened in this box. And now if I do the right thing in this box, maybe I can make 0 a trifurcation. Okay, so basically now I have some doubts about if this is the right number and if this is the right notion. But let me do things in dimension 2. Okay, I think this will be right. Okay, so sorry. It looked very right when I prepared the lecture. Okay, so let me say K, and this will depend on D, and I will make KD very large. 3 of them touch So let's see what we need. Okay. So basically what I want to make sure is that I can find a path of edges that connect these three things to 0. Okay, so in dimension 2, basically, the only thing that could prevent me from doing that if I had 3 components that touch over there, okay, because I'm only allowed to use edges inside the box, then it would be difficult to make everything touch 0, making a trifurcation here, because this blocks this one. Okay, so this is the kind of thing we want to avoid. Yeah, okay. So I think basically this is, okay, maybe this is fine if we just avoid the corners, but I have to be careful about this. Okay, so here is the plane. If x1, x2, x3 belongs to N, I can find 3 distinct, what, 3 non, okay, 3 paths, not sharing vertices. that link xy to 0. Okay, this is just a geometric fact about the lattice. Okay, so I think on the square it's obviously true. And generally, okay, what would I need? Yeah, no, I think I think this is fine. Okay, what's the worst thing that can happen? Okay, so let's assume that this is true. I will do my homework, and maybe Friday I give you a convincing argument of why this is true, like an algorithmic construction of the path. Okay. Okay, so now basically I call, let's say, W the edge configuration on En, where these three paths are open and other edges are closed. Okay, so what I know is that this configuration, it has positive probability. It has a positive probability, which is just 1 minus p to the number of closed edges times p to the number of open edges. Okay, so now what I claim is that the probability that 0 is a trifurcation, well, this event it contains the event that, well, W equal to W intersected with Fn. Okay. Okay, well, of course, I can find x1, x2, x3 such that the probability of this is positive. Okay, Fn is just the union over x1, x2, x3 not being corners of these events. Okay, so now I'm using independence. So this is equal to the probability of V restricted to En is equal to W times the probability of Fn x1, x2, x3, and this is positive. Okay, and okay, maybe now you can see where how we are coming slowly to an argument concerning the volume. So we have proved that 0 is a trifurcation with positive probability, but now we know that, well, because of translation invariance of the probability measure, the probability that X is a trifurcation is the same as the probability that 0 is a trifurcation. Okay, if you read. Probability X. This is the probability of 2x minus 1. 0 is a trifurcation. Okay, so let's call this quantity, I don't know, chi. What this tells us is that we have a density of trifurcation. Okay, so the expected number of trifurcations in in gamma n minus 1. Okay, well, it's equal to chi. Okay, I guess it's 2n minus 1 to the d, just the number of vertices that I have there. Okay, so now to conclude, basically what we have to find is an argument that tells us that basically the number of trifurcation in a box has to be bounded by the volume of the boundary of the box. Okay, and if this is true, then this gives a contradiction. Okay, and if there is a contradiction, this means that the probability of having a trifurcation is 0, which means that the assumption that we have at the beginning that Z is equal to infinity almost surely cannot be satisfied. Okay, so now for this last argument, there is no probability involved. It's something which is kind of graph theory. Okay, so okay, so I will just look at omega restricted to En, okay, where En are, okay, it's a set of edges in E such that E intersected with gamma n minus 1 is non-empty. Okay, this means that these edges, they are in E circle n, but these edges, they are not. Okay. Okay. And now I'm going to look at, I have a configuration over there. Okay, and what I want to do is basically kind of clean this configuration. So okay. We want to find, okay, so omega, which is included in the set okay, so I want basically to extract a subgraph of my percolation configuration inside the box, but I want this subgraph to check a few properties. So what I want is that is a finite, well, okay, is a union of trees. Okay, that's what I call forest. People call forest. So I want that if I look at my omega bar as a graph, okay, it's just, there are no cycles. So the second thing I want is that I want vertices of degree 1 for the graph induced by omega bar. I want them to be on the boundary. So what I mean is that, well, my subgraph, it's a union of trees, and all the leaves of my trees, they are on the boundary. Okay, and the second thing, the last thing I want is I want trifurcation in omega r of degree. Okay. Omega trifurcations in gamma n minus 1, lambda n minus 1 are of degree 3 in omega bar. Okay, what I mean is by omega bar is just, well, the graph induced by omega bar. Okay, so is it clear what we are trying to do? So we start with a configuration where none of this is true, okay? So we have a configuration that can have many cycles. It has finite component inside the box, so particularly, I mean, there are lots of vertices of degree 1 that are inside the box. Okay, but we want to modify it in such a way that okay, we get only trees, all the leaves are on the boundary of the box, and most importantly, we don't delete any edges that are adjacent to a trifurcation. Okay, because initially trifurcation are vertices of degree 3, so we are not allowed to delete an edge for a trifurcation. Okay, so let me present an algorithm that allows you to get this omega bar from the configuration omega e. Okay, and this is the algorithm you find in Hugo Duminil-Copin's lecture note. Okay, so what's the algorithm? So first thing you want to do is make your thing a forest. So delete cycles, basically, in order to have only trees. Okay, so you first want this to be satisfied, and then you will see what you do. So okay, so the first thing we do is we put an order on En, okay, and we look at the edges E1 to En sequentially. Okay, and at each step, if omega ek is equal to 1, and if ek belongs to an open cycle, we close the edge. Okay, so what I would need to say here is okay. Here we run an algorithm. Okay, so we change the configuration omega. We start with omega 0, which is equal to omega. Okay, and then we define omega k. Okay, so we set omega k. Ek is equal to 0. So to define omega k from omega k minus 1, basically the only edge whose state we might change is Ek. And in order to know if we, okay, the only thing we can do is close the edge, okay? And we close the edge only if it belongs to a cycle, not for the original process, but for the thing we had at the previous step. Okay, so basically, if you do this, after running the algorithm once, you don't have any cycles in your graph. But the important thing to check, so after this process, there are no more cycles. Okay, because basically, if an edge belongs to a cycle, at the end, it means that, well, when it was caught by the process, when it was checked by the process, then it belonged to a cycle, so it should have been closed. Okay? So, like being in a cycle, it's something, if you add edges, you're still in a cycle. Okay? So in the end, you are not in a cycle because when you've been checked, you were not in a cycle. Because if not, you would have been closed. Okay, so this is the first important remark. The other thing is that if your edge is adjacent to a trifurcation, you want to make sure that it does not get closed. Okay, because if not, this would not be true. Okay, because there's going to be a second step, but we're never going to add edges. Okay, so and okay. So you can just check that if an edge is adjacent to a trifurcation, then it cannot be in a cycle. Okay, because if it were in a cycle, well, then it has to come back some way, and it can come back only using this edge or this edge. And if it uses one of these two edges, it means that it connects this with this, or with this, which is not something you want. So because this and this are not connected outside of these two edges, then it's not possible to have a cycle. Trifurcations are preserved. Okay, so now what we have, okay, is that if you look at omega, which is omega En, okay, what you get at the end of the process, it's a forest. Okay, a graph with no cycle, it's just a union of trees. So now what we want to do is the following. So in the second part of the process, what we want to do is to delete the leaves that are not on the boundary. So what we are going to do is to delete, well, the finite. I don't know if maybe blue is better. You want to delete the finite connected component. Okay, and you want to delete also somehow some kind of dangling hands of your trees. Okay, you want to trim this part. Okay, so what we are going to do is to run a second part. So we start from now we start from omega 0 is equal to omega hat. Okay, we start from this. And we are going to perform a second algorithm. And basically what we do is if omega ek k minus 1 is a leaf outside no, if is connected so what we do is we just run the same kind of algorithm. So we have an ordering of the edges. Okay, you can choose any one you want, but you can use I don't know, lexicograph. Okay, first you take all vertical edges and then all horizontal edges in sequence. And what you do is, well, if you encounter an edge which is connected to a leaf which is not on the boundary, then you close this edge. Okay? And now if you run this algorithm once, it will not be sufficient. But basically, you have to wait until you run this algorithm without deleting any edge. So we run this. Cardinal of En times. Okay? So basically, you check all the edges sequentially, then you do it again, then you do it again, then you do it again, until a time when you've checked everything and you've not closed anything. And this should happen before En times, okay, just because if not, it means that you would have closed all the edges. Okay, and what I claim is that, well, after you've done that, of course, you have no leaves that touch the boundary. Okay, and well, you're still a union of trees, just because deleting edges won't change this fact, won't create cycles. So really the important point is to show that you've not deleted any edge which was adjacent to a trifurcation. Okay, so well, the idea is that okay, you don't. Okay, here maybe I had to be a bit more precise here, but the idea is that well, okay, you have to check two things. In fact, you have to check that when you're at trifurcation, you cannot delete those edges, and when you delete any other edge, you don't change the trifurcation structure. Okay, so for the first part of the algorithm, actually, deleting cycles, you don't change the connectivity property of the graph. So you don't change the fact of being a trifurcation. Okay? Like, what you know is that, okay, the important thing here is that, okay, this have x being connected to y in omega, it's the same as x being connected to y in, well, omega restricted to En bar union omega hat. Okay, which is what you obtain after the algorithm. Okay? Just because when you delete an edge in a cycle, you don't change the connectivity property. Okay, basically, what you are doing is you're deleting redundancy edges that connect things twice. So you don't need them. Okay. So now, okay, the same thing is true here. When you delete a leaf, well, you don't change when you delete a leaf which is inside the box, okay, you don't change the connectivity properties unless for this vertex that you've just deleted. It was connected to something, now it's not connected to anything. But this vertex was not a trifurcation in any case, so you don't really care about it. Now the other thing, you want to check that you're not deleting edges that are adjacent to trifurcations. And, well, edges that are adjacent to trifurcations, if they are of degree 1, then they have to touch the boundary, because this is connected to infinity. This is connected to infinity, this is connected to infinity. Okay, this is connected to infinity without using these edges. So this cannot be a leaf, so So you don't delete trifurcations by deleting other edges, and you don't delete trifurcations by deleting edges that are adjacent to the trifurcation. Okay, meaning that this is true for what you obtain at the end of this algorithm. Okay, so if you call omega bar what you obtain after this second step, then we're done. Okay, so now there is a last ingredient. So I want to show that this gives me a bound on the number of trifurcations that I can have. Okay, so can I erase this, the algorithm? Are there any questions so far? So, okay, so now that I know that my omega bar is a union of trees. So, let's say T1. Okay, I'm just looking at the graph induced by omega bar, okay? And I'm just neglecting all the, when I'm not really taking the induced graph because I'm throwing away all the singletons. Okay, because there are vertices that are not connected to anything, and I'm just ignoring them. Okay, so I have a union of non-trivial trees, okay, because this is actually, maybe this is a tree, I don't know. Okay, so I want to show that for any tree, what I have is that the number of degree 3 vertices is smaller than the number of leaves. Okay, so let's admit that for a moment and see how this allows us to conclude. So so what I have is that the number of trifurcations in gamma n, it is large, it is smaller than the number of degree 3 vertices in T1 union Tk. Well, it's smaller than the number of leaves in T1 union Tk. And all the leaves are on the boundary by construction. So this is smaller than the cardinality of n. And this is smaller than, well, a constant times n to the d minus 1. Okay? So we saw that the expected number of trifurcation is of order n to the d. Now we have bounded it deterministically by n to the d minus 1. So take n large enough, you get a contradiction. Okay, so I think this is easier to prove. And okay, let's try to prove. This is not very complicated. So we are almost done. Okay, so actually, here you can just prove it by induction on the okay, you can prove it by induction on the cardinality of the tree. So if the cardinality of t is equal to 2, okay, then this is obvious. Okay, now if you know that this is true for any tree, if the claim is true for any t with the cardinality of tree is equal to, when I say cardinality of the number of vertices here. So the only tree of cardinality with 2 vertices is this one. You have 2 leaves. You have no vertices of degree 3 or larger. Okay, now let's assume that you have a tree of cardinality k plus 1. Well, it's a finite tree, so it has to has a leaf. So you can see this tree tk. No, t prime b t of cardinality k plus 1. Okay, you have v a leaf in this tree. What you know is that t minus v, okay, and by this I mean the graph whose set of vertices is obtained by deleting v and whose set of edges is obtained by deleting the edges adjacent to v. Okay, then this thing is a tree of cardinality k. Okay, and now let v prime denote the vertex here. So, okay. If v prime is a leaf, then basically the number of leaves of t is equal to the number of leaves of t prime. Okay, I'm just deleting a leaf. If this becomes of degree 2, it's not a leaf anymore, but I have a new leaf. And I'm just creating a vertex of degree 2 here, so I'm not changing the number of vertices of degree 3. Is unchanged. Okay. Now, if degree of v prime in t prime is larger or equal to 2, then the number of leaf of T is up by 1, okay, and the number of vertices of degree larger than 3 is possibly, at most, okay, up by 1. Okay, so therefore, I mean, basically, I'm writing this, but you could just have a formula related the sum of the degrees of the vertices of degree larger than 3 and the leaves. Okay, so just standard recursion. You can see that basically when you add a vertex, either these two things are unchanged, or this goes up by 1 and this thing goes up at most by 1. Okay, so this closes the proof of the main result of today, and the last thing we can do is to see just how this result on the uniqueness of the infinite component can be used to prove a continuity result for theta p. So, any questions so far? Position. So theta p is continuous on 0 and 1 minus PC. Okay. Where PC is the maximal value at which theta p is equal to 0. Okay, and in fact, there is a bit more that we are going to prove. So it is right continuous at PC. Okay, so there is one part of this which is, okay, so what we have to prove is that basically that theta p is continuous on the right and theta p is continuous on the left. And one part is really relatively easy. It is the continuity on the right. And this does not use anything. This does not use the uniqueness. So if you look at theta p, okay, well, it's the probability that you're connected to infinity, that 0 is connected to infinity. It's also the probability that 0 is connected to infinitely many points. So for this reason, it's the limit when n goes to infinity of the probability that 0 is connected to the boundary of the box of size n. And now I will call this theta np. And this is a sequence of decreasing events, a decreasing sequence of events. Okay, so for this reason, this sequence here is decreasing. Okay, if you're connected to the boundary of theta n plus 1, then you're connected to the boundary of theta n. Okay, your path at some point will intersect the boundary of theta n. Okay, so now what you have is that theta np is a polynomial in P. Okay, why? Well, this only depends on what happens inside the box. Okay, so this is the sum of probability of edge configuration inside the box. A probability of, okay, so this is the sum of the probability of configuration inside the box so that this is true. And the probability of a configuration is just p to some power times 1 minus p to some power. So it's a polynomial, so theta np is the sum of polynomials, so it's a polynomial. Okay, so in particular, it is continuous. Okay, and okay, now there is one way to say this, which I'm not sure. Okay, probably you know better than me. So I think I'm not, okay, so if you're continuous, in particular, your upper semi-continuous, and I think a decreasing sequence of upper semi-continuous function is upper semi-continuous, or something like this. I don't know if it works for upper or lower. And basically, right continuous for functions that are increasing in P, this corresponds to continuous on the right. Okay, so because I forgot a bit about this part of the analysis course, I will just do it manually. It will be easier. So we just want to show that this is continuous on the right. So we are going to, okay, so let's fix P and epsilon positive. So now we choose N0 of epsilon such that theta N0 of P is smaller than theta P plus epsilon over 2. Okay, this you can do because of this. The second thing, you can fix delta of epsilon, okay, which also depends on N0, but N0 depends on epsilon. Such that theta N0 P plus delta is smaller than theta N0 P plus epsilon over 2. So here I'm using the continuity of theta N0. And now I'm done because I can just say, well, theta P plus delta is smaller than theta N0 P plus delta. Okay, just because this is a decreasing limit. This is smaller than theta N0 P plus epsilon over 2. And now this is smaller than theta p plus epsilon. Okay, when I'm first using this and then using this. Okay, and now I'm done, because if it's true for delta, okay, then it's true for anything that is smaller than delta, just because theta is increasing. And the bound from below is, of course, obvious. Okay, so my function is continuous on the right, and this is, here I've not used much. Okay. Now, continuity on the left, well, okay, here I have to put some question mark here. I'm not sure that I have a jump. Okay, in fact, everybody is pretty much sure that there is no jump, but they don't know how to prove it. Well, okay, so for continuity, basically, I have to exclude the point PC. So what I'm going to assume is that I'm going to prove continuity on the left at P0, but I'm going to assume that P0 is larger than PC. So fix P0 larger than PC. And we want to show that the limit when P goes to P0 minus of theta P is equal to theta P0. Okay, so.
Sorry.
Yes?
I didn't get the second inequality. P of P plus S.
No, it's delta. It's delta, it's delta.
Phi is decreasing, right?
Who is phi?
Theta, sorry.
Theta is increasing. It's increasing, yes. The more open edges you have, the more you're connected. It's increasing in theta and P is increasing in P, decreasing in N. It's right to question my inequalities. They are wrong 50% of the time. So,
if it's decreasing n, theta in 0 is less than or equal to 0.
yes, this is why we are using this. This is why you go from epsilon over 2 to epsilon. Okay. So this is epsilon over 2 plus epsilon over 2. Okay. So, okay. Here I'm using monotonicity in N. Okay. Here I'm using this little, okay, I'm using 2, and here I'm using 1. Okay, so now for continuity on the left, there is nothing to prove in this part, because when P is smaller than theta P, we know that theta is equal to 0. So now we want to prove this. And the argument goes as follows. So what we are going to do is to use the standard coupling. So if you remember the second lecture, okay, we constructed omega p from IID uniforms for all p simultaneously. Okay, so now I'm going to use this, and I'm going to define Cp as the unique infinite. Okay, C. Okay. Yes, the unique infinite connected component. Okay, and by this I mean I just consider this as a set of vertices. Okay. So now I'm setting P1 to be equal to PC plus P0 over 2. Okay, just a number which is between P0 and PC. Okay, and I'm fixing Y that belongs in C P1. Okay. So now what I have is that for P, okay, for P larger than P1, what I have is that 0 belongs to CP, 0 connected to infinity. It's the same thing as 0 connected to 0 belongs to CP. And now comes the trick. This is equal to, okay, this is, what should I say? Okay, so this is not equal. Okay, so this is not equal, but if I'm assuming that I have only one infinite connected component, then this has to coincide with this. Okay, because I know that Y is connected to infinity, because deterministically, okay, I have that CP1 is included in CP. Okay, I mean, this is not the case if I don't have this, but this has probability 1. So I can take this intersection. This won't modify any of the probabilities. So on this event, I have this. And if I have this, this means that as soon as 0 belongs to CP, then it's connected to Y. Okay? So in particular, okay, so what you have is that if 0 is connected to Y in omega p, then there exists a path of edges from 0 to Y with UE smaller than P. Okay, so now basically using A and B, what I have is that, so theta p 0 minus theta p, if p is smaller than p0, it's equal to the probability that 0 belongs to cp0 minus the union for p smaller than p0 of cp. Okay? Okay, so, sorry, this is equal to this. Okay. sorry, so minus limit when p to p0 minus of theta p. This is equal to p 0 in Cp minus the limit when n goes to infinity of 0 belongs to Cp. Now, this is a this is, let's see. This is this is an increasing sequence of events. Okay, if you, okay, sorry, there is no n here. It's p larger than p0 minus. So when I increase p, okay, this, okay. Infinity, okay, p0 minus 1 over n. Maybe this makes more sense. I want to make sure that I have a countable union here, okay, not to show you that I'm not doing anything wrong. So now this is, okay, I have a countable union, so I have an increasing union, so this is the probability that 0 belongs to the union of n larger than 1 of C p0 minus 1 over n. Okay. And I can, because this event is including in that one, this corresponds to the probability of the difference of the two events, and the difference of the two events is exactly the probability of 0 belonging to the difference. Okay, and now you can check that this union is exactly the same as this one, just because Cp is increasing. Okay. So now, you see that if 0 belongs to this set, then, I mean, I know because it belongs to Cp0, I know that I have a path of edge such that UE is smaller than P between 0 and Y. But because it does not belongs to Cp for P smaller than P0, I know that on this path of edge, I have an edge for which UE is strictly larger than P. And this is true for every P. So I know that for on this path that is linking 0 to Y, there has to be at least one edge for which UE is equal to P0. Okay? Because if not, this would be open for some omega P with omega P smaller than P0. Okay, so now, okay, just because of B, this is smaller than the probability that there exists E in E such that omega E is equal to P. Okay, I mean, Y here is random, so I don't want to say anything about it there. I'm just saying there is an edge in my lattice such that omega E is equal to P0. Okay, for this to happen, really, okay, and here I'm basically, it's this point where I'm using uniqueness in a strong way, okay? Because if not, basically, I could not reduce connection to infinity to a finite path. This is the important part here. And if you have an infinite path, then you would say, okay, on my infinite path, I know that the supremum of the omega E has to be equal to P0, and this does not seem impossible. But on the finite path, this supremum is a max. Okay. E. And, okay, this is a union bound, so I can say this is the sum over E, or the probability is that UE is equal to P0, okay, just because I have countably many edges. Okay, and this is equal to 0, okay? So the probability of, okay. The mass of a point for Lebesgue measure is equal to 0. Okay, and this ends up the proof of continuity. Okay, so now what about theta PC? So theta PC, we have seen that it's equal to 0 on the tree. We are going to prove that in this course that theta of 1/2 is equal to 0 and PC equal 1/2 on Z2. And something more is known, actually. So what people know is that basically, okay, so trees are graphs without cycles. And cycles make your life difficult, okay? Basically, cycles make the structure of self-avoiding paths non-trivial, and this makes the combinatorics much more difficult. So, and the idea is that in high dimensions, cycles are rare, okay? So this is, a way you can see that is that, okay, for instance, if you take a simple random walk, in dimension 1 and 2, it will come back to the origin infinitely many times, but in dimension 3 and more, okay, the probability of making a loop to the origin becomes 0. Okay, and if you, okay, so now if you look at loops that are not at the origin, you have to go to a higher dimension, and if you take other structure, you have to go to even higher dimension not to see cycles. But the idea is that because of this, high dimension things look like tree. Okay, and what people have shown is that when D is larger than 11, basically on percolation, theta PC is equal to 0, and really the reason why is that ZD for D large behave like a tree. Okay, and what D large means really depends on the kind of process you're considering. And the idea is that for percolation, basically, for D larger than 6, things should work. So the thing is that, okay, so basically the argument there is here, it's completely certain that it does not work for D equal to 5, 4, or 3. But so far the computations makes it work only for D larger than 11. But maybe there are some hopes that someday it should work for starting from dimension 6. Okay, so this is okay, people that have started to prove this in the 80s, so in the 90s. So I think these people proved it for D larger than 60, and this has been reduced to D larger than 11 relatively recently, like 10 years ago. Okay, so now the question is what happens in lower dimension. So people believe that theta of PC is equal to 0 in dimension 3, but this is a very challenging open question. And you will get famous if you solve it. But, well, a kind of frustrating fact is that if you look at the half space, Okay, so you can define percolation on the half space. Okay, you can define a critical P. It's not translation invariant, but it does not really matter. You can just define theta P as a probability that the origin is connected to infinity. And for this, it's known that PC is the same as for Z3 and theta PC is equal to 0. Okay, so it seems like a very close result. It looks like very difficult that you would have an infinite connected component in the full space, but never in the half space. But somehow, okay. It's still an open problem. Okay, so I will stop here. Okay, maybe there is no time for questions, but please save your questions.